Uh, what an honor to follow Regina, and she's amazing. She was a pioneer. The very first meeting I went to, I was still a grad student at MIT. This would have been about 1980 or so, and some NSF-funded people showed up, and Regina was among them. In those days, you can imagine she was the only woman in the room, and she told that story about the French finger that she just repeated today, and obviously, I've never forgotten it. I was really delighted to hear that she shared it with all of you. Anyway, do I get that 30 seconds back? Okay, let's see if this works. So I wanted to back up a little bit and think about the big picture. Why do we build robots? Well, they're cool, they're fun. That's for sure. They are also useful. They're whole industry, multiple industries dependent on them. But I think the main reason for us in research is to learn. And so when I started in warehouse robotics, I was excited about it in part because it was a chance to learn some new things. And so let me just back up. When I was first getting started, a lot of the work was going on in the blocks world, a sort of contrived environment that people all over the world were working on. And so you can ask the question, okay, in that task domain, what did we learn? Pick and place, I guess, popped up in that domain. There was even a French group that did a proof of the completeness of pick and place over, with a certain set of assumptions. It was in that context that Tomás Lozano Perez and Mike Wesley figured out configuration space would be a good way to do motion planning. And I'm sure we could come up with a lot more if we worked at it. There's another domain, the factory. In factory automation, what did we learn? Well, one thing about it is they were doing precision assembly tasks that far exceeded the precision that was available from an arm. And so one of the things you learned was to use contact to get precision. Contact was necessary, not something that you wanted to avoid. And but that means you need to do compliant motion. So there was some interesting work in compliant motion in those days by Neville Hogan, and Dan Whitney and his group, and I did some work in that area, and then using contact for precision. And when you look at that contact, you need to look at the forces too, and Dan Whitney and his group did some really interesting work on how do you do a successful insertion of a peg in a hole, which it turns out also applies to the question of how do you open and close a drawer. So, the lessons that you learn in these task domains can be quite a bit broader than what you anticipate. And that's what I'm hoping is the case in warehouse robotics, and that's what I want to talk about today. So what are we learning in the warehouse? Well, one thing is that it's not just pick and place, that it's actually useful to do pick and drop. And I have to say, when I realized this, I was quite annoyed, because for my entire career, I had been annoyed by people who worried about how to grasp things, but didn't worry about what they were going to do with the thing. And I always thought, well, there's no point grasping something if you haven't anticipated the next step in the process. But you know what? In the warehouses, a lot of times, all you want to do is drop it. And so I guess they were right all along. But the main thing I want to talk about today is clutter. And I think we need a greater appreciation of clutter, and I think I'm learning that in the warehouse. So, in order to share that with you, I have to give you a full and complete explanation of how logistics works. That's no problem. I think it'll take about 90 seconds. Let's see. Here's an example. You want a mint, and the mints are made in a factory like 1,000 kilometers away. And so you call up the factory, you say, I want a mint. They say, no problem. They hand it to a courier, and the courier shows up at your door several hours later. Says that'll be 1,000 euros, 3 cents for the mint and 1,000 euros for the transportation. Okay, probably not the best solution. Instead, we use ride sharing. And that's really what logistics is. It's ride sharing for stuff. Okay, instead of putting a mint in the courier's hand or putting a mint in a truck, you put a gazillion mints in a truck, and now you've amortized the cost of transportation. But in order to make that work, you have to mix the loads, right? You can't just have a zillion mints in a truck. And you also need to have various levels of containment so that you can sort these things out at distribution centers. So at the factory, they put the mint in a roll, they put the roll in a box in the case, et cetera, put it on a truck with a bunch of other stuff. It goes to a distribution center. Now it's broken down a level or two, sorted, then put back into more containers, and now another truck drives it to another distribution center. And this process continues, and it continues even when it gets to the store. Right in the back of the store, they break things down, and then it continues with the consumer. So you're wandering up and down the shelves, and you're picking things off of the shelf, putting it in your own bin, and then taking it out of that bin of the checker, et cetera, et cetera. And then it even continues at home. But we'll get to that in a second. So that's the ride-sharing game. It does use this progression of container sizes, and that gets to the issue of clutter. Okay, so this is the way I used to think about clutter. You've got at the no clutter end of the clutter spectrum. It's just I guess that would be relevant in 0G. Usually you've got at least a little clutter because it's on top of a table or something. And then what I used to think of as high clutter would be like stuff in a bin. That looks horrendous, or it used to look horrendous. But then it turns out maybe that's high clutter, but we need another term. And I just made up the term dense clutter. No point Googling it. I don't know if anybody's using it or not. But it's beyond what we used to think was high clutter, because you've got that stuff that's in logistics, I've discovered they call it tiling. So if you've got a bunch of boxes that are tightly packed together, so it's hard to get your fingers in at the edges, okay, they sometimes call that the tiling problem. And then you've got, of course, this progression of nested containers, which is a whole nother thing. You can look at this tiling thing as sort of the cigar box problem. How do you get the first cigar out of the cigar box? And you can look at this nested container thing as the Russian doll problem. So, okay, so now I said we wanted to talk about the last bit, where you are dealing with the stuff at home. And after spending some time in the warehouse, going back and forth, it occurs to me that the same things that happen in logistics are, to some extent, happening in your house. Now, in logistics, they love to say, we don't ship air. Okay, that's why they want to pack things so tight. They don't want to waste the truck or any of the other stuff on boxes full of air, unless it's potato chips or breakfast cereal. I don't know why there's exceptions for those things, but that's a commercial thing. If you look at the boxes of the bins and everything, there's as little air in there as possible. Now, in your house, you don't say, oh, I don't want to store air. You never said that, right? On the other hand, you don't have your books separated by an inch on either side so you can get your fingers in the bookcase, right? You want to get as many books in the bookcase as you can, and that's the same thing as minimizing the amount of air, okay? And so everywhere you look in your house, if you really look, with a fresh eye, with a roboticist's eye, I'll say, and look in your kitchen cabinets, look in your drawers, look in your dresser drawers. If they're like mine, they're stuffed. Okay, in other words, I'm not storing air. I'm storing as little air as I can. Now, in factory automation, we often talked about structured environments, and everybody agreed that we wished we didn't need them. The engineers would figure out a way to have no clutter, and that was part of having a structured environment. But in your kitchen, it's a little bit more than that, okay? Because what happens, let's say you're getting ready to cook, you take some stuff out of the drawer, you take out the spoon and the spatula and a knife or whatever you need. Okay, so when it was in the drawer, it was structured for efficient storage. Now it's structured for efficient use, so you can very quickly use what you need and change tools and everything. And at the end of the meal, you're putting that stuff back in the drawer. So your stuff is constantly going back and forth between the structured for use and structured for storage thing. So That's the message. Respect clutter, okay? Dense clutter is good because it means efficient storage, and I wish I had time to tell you what we're doing about it. This is my former student Xiangyi Cheng's PhD thesis, and so you can look at some of those things if you want, but I have no time to talk about it, right? Thank you.
Stage mic volume every time. Turn this up, please. We have time for one question, and the question can be, what are you doing about it?
I can
Any
answer
questions?
that question. Unless...
All right, then I'm going to pose the question while Peter sets up. What are you doing about it?
Well, what Xiangyi Cheng is doing is she's looking at what are the choices for where you're going to put your fingertips on the accessible surfaces. Many of the surfaces might be covered by things. So if it's a book in a bookcase, she'll examine the possibilities where you might put a fingertip. She looks at all possible contact modes, at all possible contact points in the environment, as well as between the robot and the object, and then using probabilistic motion planning to find sequences of motion. So it's autonomous planning for dexterous manipulation, including all those contacts that you get in dense clutter.
Let's thank the speaker again.